I would like to talk about some robust variants of principal component analysis. Principal component analysis is classical machine learning techniques. It is widely used in order to, for example, in order to decompose the data in data sets, in order to reduce the number of the features. The classical principal component analysis have some formulations. I will follow the formulation that leads to Pearson. It formulated as follows. We try to find n-dimensional hyperplane in n-dimensional Euclidean space so that the sum of Euclidean, the square of Euclidean distance from the points to that plane are minimal. This solution is reduced in the sequence of sub problems. The first, we try to find the center of the cloud points, what are 0. It's we found it as a solution to the problem as a center. The center R is such point that sum of the square of Euclidean distances are minimal. No, the solution is well known is an average of the points. After finding the center, points are centered. We try to move our axes to the the center of the axis system of coordinates to this center. After that, we try and one by one sequentially find the principal components. They are searched by solving the following problem. We're trying to minimize the mean average of square distance from the points to the line that are with the vector A as A with the norm equal to 1. This vector is the direction vector for the line. After finding the vector AG, we perform transformation. It's a projection to the orthogonal subspace. This task is always reduced to the as known to the task of finding principal components and the agent values, agent vectors and agent values of the positive symmetric matrices. S is a covariance matrix. In order to solve these equations, we can apply a well-known iterative process. The problem can be erased. I show some picture in order to if the data contain outliers. Well, for example, we can see some points on the plane. The left one is from the well-known data sets with points are presented that on the axis x is a logarithm of effective temperature, on the y logarithm of the lightness of the star. Is the data set about from some about stars from some we see this. We have 4 and 2 points that are may be considered as outlier. If we try the classical percipient component analysis with what dotted line, they rotated to in the direction to the outliers. And the same behavior we can see on the right picture. Значит, another example from the another diagram for stars collection data sets. We can see that points are directed around the line, and some points outside of them. If we try classical principal component analysis, we can see the same behavior. Axis principal components are rotated on the direction to the outliers. How to solve the problem of the outliers? In our work, we use the approach that we used for another tasks, for regression, classification tasks, for clustering. This approach is based on the replacing of mean average function for the estimating of the mean values by the another functional that estimate the differentiable estimation of mean values. If the m is differential estimation of average value, if we use such a functional, then the problem of minimizing functional q in order to find parameters a will be the center of the points and the vectors for principal components. Then the problem can be reduced to the sequence of the tasks. Each task minimize for functional that similar to average, but it's minimize the weighted average of the values. The weights are what we can see the problem. Weights are v car. At each step t, weights are equal to partial derivatives of the functional on-path argument. Now, there are some examples of such estimation. The first is a so-called M-mean. M-mean can be considered as the center of the points on the real line. Z1, Zn are the values, points on the line. The center is such point U, that's the sum of estimations of the distance between U and ZK are minimal. For example, if rho is a square function, we have mean average, class ordinary mean. If rho is a absolute value function, then we have a median estimation. In order to, if rho is twice differentiable, then we may define a mean estimation that is differentiable. That is important for gradient iterative algorithms. In this work, we use a smoothed variant of the mean average of the median. It can be constructed if we use, for example, rho epsilon r is equal to square root of epsilon square plus rho square. If epsilon is small, then we can we have the smooth variant of median that has derivatives and differentiable. Another example is the sum of values, but before we summing, we use we censoring the arguments. Arguments are greater than the threshold value are replaced by the threshold value.
There are 5 minutes left. 5 minutes left.
Да. We select the threshold value as smoothed by the smoothed variant of quantile. Smooth quantile estimation can be maybe defined using such rho function. Rho alpha when R are negative, we raw function that used for smooth median, for constructing smooth median, multiplying on 1 minus alpha. When R are positive, we multiply just on alpha. So this method we use to formulate the robust variant of principal component analysis. So in the formulation for the task for finding the center of the cloud points, we replace the mean estimation by the robust variant of the mean estimation. This problem is reduced can be reduced to solving such a nonlinear equation that can be solved using iterative algorithm. It's at each step we calculate weighted sum of the points. The weights are equal the partial derivatives of 4 square distances from the center estimated at step t from the points. After center was found, we solving the problem when mean estimation we replace by the differential robust variant of mean value. When in calculation we used censored variant of mean estimation. This the following. Так. Вот CP alpha. This functional. The problem of finding the principal component is also reduced to the system of matrix equation, similar to equation that we solved for classical principal component analysis. They differ from that by in our case when we calculate the covariance matrix ST, we use also diagonal matrix. On the diagonal are the weights. Weights are calculated as partial derivative for distances from the points to the line with vector direction vector a t that we founded at the step t. The same iterative algorithm to find.
Time is up. Please go to the conclusion.
Here the examples. These examples are illustrative. We don't try to calculate some numbers. We try to make a picture that explain visually the benefit of our method. This another example when we try to use our approach and project the data on the first, second, and third principal component, we can see that the data are divided into clouds that have directed along some straight line. We can then apply the clustering regression in this case. Another variant for the data set using is a robust approach. We see that our cloud projections points are directed stronger along the axis. In classical variant, the cloud plonks is rotated on somewhat. Conclusion. We formulated a new algorithms to find robust robust formulation for the task of finding principal components, and on the illustrative examples we tried to show the effectiveness of our approach. So I thank you for your attention.
Thank you. The questions, please. Okay, I have a question. Are you the first who actually did the robust version of PCA or not? Is it the first research or do you know something similar?
Of course, it's not the first research. There was another research on this area, but what's the main difference of this research from the others? This research is different in has I'm try to find robust formulation for the task of finding principal component analysis, starting from the classical formulation, and try to explain that such formulation leads to robust variance for PCA component analysis. I don't see in other works such approach. They used different approaches to find different approaches from our for formulation of the problem.
Okay, thank you. More questions? If so, thank you very much for attending. Our session is closed.
Thank you very much for your attention.
Thank you for your